fun fun. You had the skier that was like this. You had a skier that was going along at a certain speed. I think the speed was given, right? Speed was given. Yeah, it had to be given. So he has a certain speed down here. We'll call this V initial. And then you want to know what is the final speed when it gets to the top. Now, this problem isn't any different from the ones that we've been doing so far, except there's an added complication. So on this problem, the way you'd say is you'd say the kinetic energy here is equal to kinetic energy plus the potential energy up here. And so as a result, the kinetic energy will be less than what it was down here, so you'll have less speed. So you'd have this height, I'll just call it h, you would say 1/2 mvi squared, that's the initial kinetic energy, is equal to 1/2 mvf squared, that's the final kinetic energy, plus the potential energy, final, which is going to be mgh. Okay? But there was a complication on the problem because there was a frictional force on this incline. And so as the skier is going up, he has this kinetic frictional force. He has a kinetic frictional force acting upon him. Now, this acts over a certain distance, and you can figure out what that distance is using your trig functions. That frictional force acts over a certain distance. When this frictional force acts over this distance, it does work on the skier, and it takes away energy from the skier. So I'm going to have an extra term here. How's it going to work? I'm going to have I'm going to get rid of this and say instead I have my kinetic energy. Or wait, no, let's not do it that way. Let's put it over here, plus the work that I have over here. No, because then it'll be negative, or make those values bigger. No, let's take it to the other side. The point is it's taking energy away. So I'm going to rewrite this over here to be kinetic energy initial plus the work that's being done by the frictional force. That's going to take energy away from the initial state, and so it'll cause this velocity to be less. Now, you have to figure out what is the frictional force. That's previous chapter. Remember, our normal force, if I have an object sitting on an inclined plane, the normal force is here. If this is my angle theta, then this is the component of the weight, which is going to be Fw sine of 90 minus theta. You have to find the normal force, and then once you find the normal force, the kinetic friction is equal to mu k times that normal force. Okay, so I'll step back through the steps. It's a challenging problem, and not going to see one like it on the test. For your quiz, it's a good problem for you to work for your quiz. But let me step back through it. You have a skier that is traveling along at a certain speed. He has a certain amount of kinetic energy. When he goes up the slope, he loses a certain amount of energy. And so that's why I added in this work. Now this work is positive or negative? Negative, right? Because the frictional force will do negative work. So it's going to be some value here, 1/2 mv squared, minus some value here. And this value will be the frictional force times the distance over which it works. So the work done by the frictional force will be Fk times d. D isn't given in the problem. You have to figure out what d is, but the angle and the height h is given, so there's a triangle here. You can determine what is the hypotenuse of that triangle. Okay, so once you find out the total initial kinetic energy, you subtract the work that's done by friction, then you can set it equal to the final kinetic energy plus the final potential. some of you have done this already, you got it right, but I understand that that's a complication that we have to discuss in class. Yeah. Well, you're adding negative work. This work right here comes out to be negative because FK and D are opposite directions. And so the frictional force will be doing negative work. Okay, people? Does that give you a bump in the right direction? Please? What's different of this? Oh, yeah, the kinetic friction and the displacement are opposite directions. So the kinetic friction will do negative work. That will cause this value up here to be negative. Our work will be negative. So I wrote it plus W, but with the meaning that W is negative. So I'm taking a difference in two numbers there. It's a good problem. You're not going to see one that complicated on the test, but on the quiz, it's really just we're adding now two works, or we're throwing in the work into the energy, the conservation of energy, which isn't a big step when we think about our work energy theorem, but again, it's a complication that we have to address in class. Okay, any other questions about this? Let me know if there are. You can shoot me an email on today or after class or later today. I'll be around until 3 this afternoon, about 1:20-ish, 3. Okay? Any big plans this weekend? They're having a play over in
Midnight's on the Screen.
yeah. It's I think 7 o'clock tonight, tomorrow night, and then 2 o'clock on Sunday. You guys get in for $5. It's a good deal. Anything else going on this weekend? No? You got any big news for the weekend? Big event? Oh, that didn't look boring. We almost study all the time. I imagine all the other classes out on campus with, less diligent students than you are. Like they're planning parties and they're going out and doing all sorts of stuff that they probably shouldn't be doing anyway with you guys. Studying. You're right. Awesome. Okay. We have a couple more concept test questions from, we didn't wrap up last week, if I recall correctly, or I don't know, last time we were Wednesday. Somebody tell me where we left off here. $5.18. I think we just had a couple left, right?
3.
6. Did we do this one? We did that one, and we did that one. Not this one. Okay, the picture's not on here, so let me give you the picture. Paul and Kathleen start from rest at the same time on a frictionless water slides with different shapes. At the bottom, whose velocity is greatest? So let's say, gosh, I forget who's who, but we'll say that this is Paul. Paul goes down a slide like this, and Kathleen, on the other hand, she starts at the same height, but she goes down a slide like this. This is Kathleen. I call her Kathy. Okay? So at the bottom, whose velocity is greater? They are on these frictionless water slides. At the bottom, in different shapes. At the bottom, whose velocity is greater? You're doing really well, most of you. Ask around, ask your neighbor what they put if you like. Confirm your genius. Okay, we'll stop at 110. 110. Some of you might have put Paul because you thought, well, Paul travels a shorter distance right? And you would have been right in some circumstances, but since this is frictionless, it doesn't matter. There are no dissipated forces. The only forces that are acting on them are, well, gravitational force and the normal force. And the gravitational force is conservative. Since it's frictionless, the normal force is too. And so they're both going to have the same speed at the bottom. All right, Mike applied 10 newtons of force. Oh, wait, let's go back. I'm sorry, I showed you that answer. Oh, I went to black and white. Interesting. Let's do another one. Let's say, what if it's not a frictionless slide? And now Paul goes down the straight slide, Kathleen goes down the curvy slide on a non-frictionless. It has friction. Which one's going to be traveling faster at the bottom now, Paul or Kathy? Paul is the blue slide, and Kathy's the other one.
How did you change the question? Which one?
I said instead of being frictionless, it's not frictionless. It has friction. All right, I'll stop at 50. Awesome. A is right. Paul's going faster because the friction acts over a shorter distance, and so it takes away less energy. It's a lot like the skier problem. Let's see, did I tell you the Mozart joke? Oh, I did? Did you hear about the Italian chef that died? He worked over in the culinary school. Did you hear about him? Yeah, he passed away. He didn't really work in the culinary school. I just made that up. Okay, Mike applied 10 newtons of force over 3 meters in 10 seconds, and Joe applied the same force over the same distance in 1 minute. Who did more work? I'm going to stop at 35, 38. We'll go to 40. Awesome, C is right. It doesn't matter about the time because we're only talking about work. If they apply the same force over the same distance, they do the same amount of work. Let's see, what type of ships do students study? Did I tell you I wanted to be a naval architect when I was, 19, 18? I did, I want to be a naval architect. Obviously, I did not become a naval architect. But what kind of ships do students study? Scholarships? All right, so they both did the same work. Mike performed 5 joules of work in 10 seconds. Joe did 3 joules of work in 5 seconds. Who produced the greater power? Okay, we'll stop at 45. Just 2 more seconds. Okay, good. B is right. Joe produces more power. Even though he does less work, his power is 3 divided by 5. Work over time, so that's 0.6. Whereas Mike does 5 joules, but in a longer amount of time, and his work then is 0.5. So, yeah, Joe does more power. how'd y'all do on that one? Was that good? Oh yeah. So why can't your nose be 12 inches long? Because then it'd be a foot. I'm sorry. What did y'all have an alternate punchline? Engine number 1 produces twice the power of engine number 2. Can we conclude that engine 1 does twice as much work as engine number 2? Yes or no? All right, we'll stop at 35. Okay, awesome. I'm gonna use phone. What do you get when you take the circumference of a pumpkin and divide it by the diameter? Pumpkin pie. Okay, when you pay the electric company, you pay them by the kilowatt hour. What are you actually paying for? You pay Entergy for energy, power, current, voltage, or none of the above. What are the units for a kilowatt hour? Oh, all right, we'll stop at 40. 8 more seconds. Okay, we're a little bit split. We think that we're paying for power, but the answer is energy. First, if we just look at the units for kilowatt hour, remember a watt is a joule per second. An hour in SI units would also be seconds. And so the kilowatt hour simplifies to just joules. I did some simplifications there. Like I said, what is a watt second? And a watt times a second is equal to a joule, because this is a watt and this is a second. So Entergy doesn't care when you use your power, though in some markets they do care when you use your power, like in larger markets, Los Angeles, California, wherever, where lots of people live. You get charged more for using energy during the day than at night because it's a higher demand time. But around here, we just get paid straight up for the energy that we use, and they don't care how quickly we use it. We can use all of our energy on the very first day of the month, and then not use any electricity for the rest of the month, and we'll still get paid, charged the same amount. Wow. Yes. Okay, which contributes more to your electric bill each month, a 1,500 watt hairdryer or a 600 watt microwave oven? I'm going to stop at 40. Stopping at 40, just 5 more seconds. Oh, Maggie. Sorry. I'm sure you answered it right. Sorry, it's not a big deal. Everything's a big deal to Maggie, y'all, right? I'm sorry. Should never pick on students in class, right?
In class.
In class, right. So the answer is E. That it depends on how long each one is on. Right? If you use your hair dryer for 3 hours drying your hair, then yeah, it's going to use a lot of energy. But most of you don't use your hair dryer for that long at all. In fact, me, hair dryer, 6 to 7 minutes at the most. to dry this huge head of hair? How many use hair dryer? 30 to 45 minutes. So you're using up some serious energy. Your hair dryer is about one of the biggest consumers of electricity in your house. We'll talk more about that next. Okay, this is a potty joke. It could be the last one of the day, so it's like a middle school boy joke. Why did Tigger stick his head in the toilet? He was looking for food. Okay, let's just sort of recap the chapter right quick. In this chapter, you have a blank page at the end, but in this chapter, we looked at work. Work is equal to this FD cosine theta. In this chapter, you'll have some problems where you'll just have to calculate what is the work that's done. And we work some like that, like the grocery cart with the force and the distance. And there'll be some on your test that are just straight up how much work is done. You'll also need to determine, is work positive or negative? So I can have positive work or I can have negative work, depending upon if the force and the displacement are in the same direction, or if the force and the displacement are in opposite directions. I can have either positive or negative work. Remember, the negative doesn't mean direction, because work is a scalar quantity. The negative means that it's taking away energy. And then that leads us into the work energy theorem, that work causes a change in energy. Typically, we'll think of this as kinetic energy, that if I do work on an object, where my work is force times displacement, then that's going to cause a change in my kinetic energy, or will impart energy to my system. And we work some problems where I have this force times displacement, and then I can calculate what is the speed of that object after that amount of work has been done on the object. You need to know the units for all this stuff too, of course. We talked about conservative versus non-conservative forces, meaning in the sense of conservative forces don't lose energy. Non-conservative forces do lose energy. When I say they lose, like friction loses energy, it produces energy that's lost to the system. So it produces thermal energy and sound energy and other things that are no longer usable to the system. We also did the conservation of energy. And you'll have a couple of problems like that on the next test. And that's saying that the initial energy is equal to the final energy. In the conservation of energy, we'll always be dealing with conservative forces, so we'll just be looking at gravitational potential and kinetic energy, or elastic potential and kinetic energy. So you'll see probably both types of those problems. That would be like the roller coaster problem that we worked in class, and you can find in the old test. And that would also be the spring. The spring compresses, how much does it compress? That sort of business. Like problems that we worked in class, and you have some in your homework as well. And then finally, we have Hooke's law. This is the F equals minus kx wrapped up in that conservation of energy. You could have a problem, and you have some on your quiz, where you have to figure out what is the compression of the spring, or what is the force given a certain spring constant, or calculating one of those things. Remember this negative, sorry, this is a straight mark right here. The negative here is just to remind you that the force is always opposite the direction of the displacement. If you want to leave out the negative, hey, that's okay. Sometimes I'll leave it out too, because if you just want to calculate the magnitude, it doesn't matter what the direction is. And often that's really all that you want to know is the magnitude of the force. But that negative is just there to remind us that if I have a spring, and if this is its equilibrium position, but I compress the spring, my displacement is negative, but the force that the spring is pushing is in that direction. So notice I have a positive force and a negative displacement. Okay. But often we just want to know the magnitude of that force. And then finally, the very last thing was power. Power is energy or work over time. Just know the units, know how to calculate. You might have one problem about power. Not a big deal. We'll see power again next time. that's it for that chapter. The hard parts about this chapter are probably the conservation of energy. That's probably the hardest part of the chapter, is the conservation of energy, dealing with springs and with the gravitational friction. You're not going to have any problems like the skier problem on your test that have friction involved, but you do have one. Okay? So how do you feel about it? Yeah, I think it's not an easy chapter, but I think it's an easier chapter than definitely chapter 4. Certainly not easier chapter 4. Okay? So make sure that you can do all those things. You know, listen, a good study practice is for every day you just spend 20 to 30 minutes a day that you go through maybe the notes that we did in class, and then you go through some old exams and you say, gosh, these questions are similar. You have some in the back of your workbook, and try to work those all by yourself. And then go back and check your answers, see if you got them right. If you didn't, hey, you're great. Just keep moving on and do other stuff. If not, you might want to revisit that. Look at some other problems, revisit the examples we did in class, and you look in the OpenStax book and see how they approach that problem. All right, these are all good practices for any class, but also for this class. For many of you, physics is a new thing, right? You didn't have physics in high school. You might have seen some of these topics, but for many of you, you didn't have physics in high school. And so sometimes it's a different way of thinking about things, and you just have to spend daily time in that so that you're sort of get into that groove. Okay? All right. One other thing before we move on to this next chapter is, I think I told you this, but we are going to have some opportunities for extra credit coming up. We're going to have the food drive coming up. Nichols Can. Are you familiar with this? We do this every year at Nichols. You know what I'm talking about? Every year Nichols has a food drive. And I like to have my classes participate. And I ask you, I don't require it of you, but I ask you to bring in a couple of items. We'll have a goal for the class. I don't know, I have 200 students or whatever, so my goal will probably be 500 items. And if the classes bring in 500 items, say, I'm not sure that would be the value, but if they do, then we'll get a certain number of extra credit points. It'll probably be 10 extra credit points. And when we reach that goal, all my classes together, I suspect that we will reach it, then all the people in the classes will get the 10 extra credit points. I'm not requiring you to participate in the food drive because, you know, it's not really part of this class, but I think it's good to think about how we're privileged. If you're in this class, you're privileged. No matter how you think you are. I know we're all sort of different economically, but if you're in college, you're a privileged person. So some people don't have that privilege, and some people are hungry day to day. So I think it's important for us to think about those people and to help them the best way that we can. The other thing is we're going to have a couple of assessments, and both of those will also count for extra credit points. Together, they'll count for 10 extra points. So you have a total of 20 points that you can get. Now you're thinking, what are these 20 points? They don't go on your final average. They go sort of into the pot. So you can think of them as adding to one of your exam scores. Okay? There's 700 points total, I think. They sort of go into that pot. Just think of them as adding to your exam scores. Okay? So we'll have those 3 opportunities that will add up to equal 20 points total. That'll help some of you, but I don't want to mislead you. 20 points isn't a whole lot in 700 points. The best way to do better in the class is to do better on exam 3, exam 4, and the final. And don't forget those OpenStax quizzes. They count as an exam. You want to be shooting for 100% of those things. So do all that you can to get every answer right. And remember that, you know, we have more quizzes coming up. So if you haven't done super on so far, although the class has been doing pretty well on those quizzes, but if you haven't been doing super, just know that you have more opportunities to improve as well. Yeah, maybe. Oh, I'll announce it. Not until later in the month. Okay? Alright. Let's move on to the next chapter on momentum. I think that you'll find that this chapter, like chapter 5, is not easy, but easier for certain than chapters 3 or 4. We're sort of over the hump in this class. Let's just take off and we'll go lay in one of those hammocks out in the pine trees. Do y'all have one of those hammocks? I told my wife I want one for Christmas. I think they're too expensive because our Christmas budget is small. Let's see. So we're looking now at momentum. Momentum is the product of mass and velocity. We're going to write it like this. We'll use lowercase p as our variable, and it's equal to the mass times the velocity. Now notice that I used arrows over this, and that's because momentum is a vector quantity. Momentum is a vector, velocity is a vector. We have to consider the vector quantities. Now don't sweat it, because we dealt with vectors back in chapters 3 and 4. We're not going to deal with them in the same way here. So you'll find that they're a little easier than what we did with chapter 3 and 4. The SI unit for momentum is kilogram meter per second. So nothing fancy. We just take the basic SI units for M and V. There's no fancy unit for momentum. I think I mentioned this some time ago, but Newton, when he first came up with Newton's second law, we write it as F equals ma. Newton actually wrote his Newton's second law as F equals dp dt. Y'all are in calculus, right? This is, when I write dp dt, what does that mean? The derivative, right? So it's like he was writing, I'll write this sort of in non-calculus terms, the change in mass times velocity over time. So he said the force, if you apply a force, it's going to change the product of your mass or your velocity divided by time. And notice here that v over t, what is that? Acceleration is right. It is the acceleration. So this is the same as F equals ma. And that's the way we write it. But Newton, when he initially conceived of the idea, he was thinking of momentum and not F equals ma. He was thinking about how do the forces change the product of the mass and the velocity. Now, let's try this question. Now, actually first, momentum is a vector quantity. So an object can have a momentum, say object number 1 has a momentum that's equal to mass times its velocity. And then I can have another object, object number 2, that has a velocity in this direction. Now we'll talk about the momentum of a system. So if I were to add, if I had these two objects had the same mass and they also have the same speed, what would the momentum of that system be? It would be 0. Because even though they're both moving, one's moving in one direction, one's moving in another direction, this object would have plus mv, this object would have minus mv, because the velocity here is in the opposite direction. So we'll see that we can have a system of particles when we add up all of their momenta. We'll add up the momentum for each individual particle all together, and then we can say that the total momentum will be 0. Or it could be 0, it doesn't have to be. But in this case, it would be 0. So with that in mind, let's keep this, let's try this problem. Collection of particles has a total of kinetic energy of 0. What can we say about the momentum of that system? Okay, doing well. Few of you have an incorrect answer, but feel free to ask around and ask your neighbors what they put, okay? And we'll stop at, say, 42. 42. Okay, good. C is the right answer. If it has a kinetic energy of 0, that means that nothing's moving. Because remember, kinetic energy is a scalar quantity. So this whole thing, this argument that we had up here, about if I have one particle moving in one direction and one particle moving in another direction, the kinetic energy of this, not 0. Because they don't add up like vectors. They add up like scalars. So these two particles would have kinetic energy. In order for them to have no kinetic energy at all, everything has to be not moving. So here, the momentum is 0 because the particles are not moving. Could we say the same, the reverse, rather? Could we say that if the momentum is 0, that the kinetic energy must be 0. Can we say that? No, because if the momentum is 0, that doesn't necessarily mean that they're not moving. That they can be moving, but just in opposite directions such that their momenta add up equal to 0. Okay, let's see. Did you hear about the Energizer Bunny? He was arrested. Did you hear about that? Yeah, battery, arrested for battery. Okay, so Newton's second law, I'm sorry, this is what I'd already written. That is that F is equal to ma, which is equal to m delta v over delta t, which is equal to delta p over delta t. So our force is equal to the rate of change of momentum. So we can say that our force, by Newton's second law, and by this little argument, or not an argument, by this equation, our force is equal to our rate of change of momentum. So you're going to see some questions on the exam where you analyze a situation and you figure out how has the momentum changed. And the momentum changes in a certain amount of time. And by that, by calculating how much the momentum has changed, and then figuring out how much time it took for that momentum to change, you can determine what is the force that was at work. This is very useful because it's very difficult to measure forces. Have you ever thought about this? It's not that easy to measure a force. You have to construct some sort of device, like a scale or something along those lines, to measure the force. And anytime you use a measuring device like that, it's intrusive and it changes the system and how it works. So it's kind of difficult to measure forces in systems, but it's very easy to measure their mass, and it's very easy to measure their speed and how it changes. So if we can calculate this, then we can determine what is the force that's at play. Let's try a problem, I'll show you. Or just the first couple more definitions. We're going to define the impulse as the change in momentum. So I is going to be equal to delta P. I is just the impulse. I'm not really going to use this term very much, but other books do, and if you take the MCAT, you might see impulse. Don't let impulse fool you, it's just the change in momentum. It also, because we have this F equals delta P over delta T, if I is equal to delta P, then I is also equal to F delta T. Y'all follow how that works? Because delta P is equal to F times delta T. The impulse also is F delta T. So both of these things are true. If I were to plot F versus T, and it looks like this, you know, say, the impulse would be the area under that graph. The impulse would be the force times the delta T. It's the integral of F delta T. So let's look at this collision problem. Listen, when I was a kid, we had this 1964 Ford pickup truck. Y'all know the 1964 Ford? It was a fleet side, which wasn't real common back then in the 60s. And it was also a long wheelbase, which wasn't common. It was a really nice truck. But my dad had bought it when he was a teenager, and then he had it until, I don't know, I was a teenager. But towards the end of its life, it wasn't working very well, and I don't know, we just sort of used it out in the country, and it didn't really matter that it didn't have certain things on it, you know, like air conditioning or the windows wouldn't let up. I mean, it was an old truck, so it didn't have air conditioning. But it just didn't have some of the amenities. Like, for example, it didn't have brakes. And so whenever we take the truck out to do whatever it is that we were doing it, we always come back to the house and we would gear it down. I don't know how to gear it down. Gear it down so we go to third, to second, to first, to make it go as slow as possible. And then we would have this big oak tree. We'd run into the tree. Do y'all do this? No. It's Mississippi, right? Anybody from Mississippi? Megan? That's Megan. Where are you from? Oh, but you're a coastie though. That doesn't count, right? Oh, West Point. Yeah, y'all do that in West Point, right? Yeah, I used to live in Starkville. But, so anyway, we run into a tree. And the bumper is steel bumper, so it wouldn't affect it. It hurt the tree more than anything. But we can figure out if I'm going at a certain speed, and that change in speed happens over a certain amount of time, we can imagine or we can calculate what are the forces that it takes to, to stop this 1-ton truck traveling along at 3 or 4 miles an hour to stop it in a certain amount of time. So let's look at this collision. This is a similar thing. I have this lady driving this car. The car has a mass of 1,000 kilograms, and it's initially traveling at 10 meters per second to the left. Now, on these problems, you need to be very careful with your signs and make sure that you get your signs correctly, because momentum is a vector quantity, and so the directions are important, and they will change your answer one way or another. If you get the signs wrong, then you'll get a wrong answer. That will be in the options probably, because I'm such a jerk and I do that. So this car is traveling at negative 10 meters per second. It's to the left. It hits a wall, and then it bounces back a little bit at 2 meters per second. We estimate the time that it takes for the collision, say 1/10 of a second. These collisions don't take very long. I want to know what is the force that is imparted to the car. Well, I know that my impulse, which remember is my change in momentum, that this is equal to mass times the final velocity minus mass times the initial velocity. And that further, this is going to equal to my force times delta t. All I've written here is delta t equals F delta t. Now I want to figure out what is the force. So the force is m times vf minus vi. I've just factored out that m, remembering that these are vectors, divided by delta t. My mass is 1,000. Vf, that's my final, is going to be plus 2 meters per second, minus Vi, which is negative 10 meters per second, divided by my time, which is 0.1 seconds. And so that's going to be 12,000, because this becomes plus 10, 12 times 1,000, divided by 0.1, which is going to be 120,000 newtons. That's a pretty big force. I mean, this car is going pretty fast. 10 meters per second is a zoom in, but you remember, let's see, 100 miles an hour. Y'all remember what that was in meters per second from the Gone in 60 Seconds problem? You know, I remember it was about 50 meters per second. So 10 meters per second is about 20 miles an hour. So she's not going real fast, but that's still a big force, 120,000 newtons. A largest person weighs about 1,000 newtons. So that's like having 120, football players sitting on top of you. Okay? All right. So you'll definitely see a problem like that on the test. Let's try one of your own. There's some in the homework too. Oh wait, no, I have another collision video. Well, let's do this one first. Let's do this quick test, and then we'll go back to that video and look at it. right, we'll do about 15 more seconds. 2:15. $2.15. Okay, I think D is right. Let's see. I want to know the magnitude of the acceleration of the football. Well, there are actually a couple ways you could do this. Let's do it the hard way first, and then we'll do it the easy way. The force is delta P over delta T. All right, so I can figure out the force first. The force, and this is the hard way, okay? But then you need to know how to do this problem too, so let's do this one as well. Delta P is going to be M times delta V over delta T. That's going to be M. It's going from 10 meters per second to 0 meters per second. Here, I don't really need to worry about my signs so much because I got that 0, so I don't have to worry about am I subtracting a negative or adding a negative or whatever. So I'm just going to forget about the signs in this problem and just write, I'm going to write 0.5 kilograms, 10 meters per second, because that is my change in speed divided by delta T, which is 0.04 seconds. So that's 5 over 0.04. Does anybody know what that is? 125? 125 newtons. So the football player, he exerts a force of 125 newtons in order to stop the football. And then we want to know the acceleration. Well, A is equal to F over M. So that's 125 over 0.5 kilograms newtons. So that's equal to 250 meters per second squared. So he causes an acceleration of 250 meters per second per second. But the easier way to work this, actually, is if you know the change in speed and you know the time over which it occurred, that's also your acceleration. So you can try that on your own, but if you divide these two numbers, that's also equal to 250. I mean, you can see that because I took half of that and got 125. But these two, that's an easier way to work that problem. But you do need to know how to calculate the force. And the force is this delta P over delta T. You will see a problem like that in this chapter. In fact, there are really only two types of problems in this chapter. This one, and then the one that we'll work next time with conservation of momentum. Okay? We will come back to that video. Let's do a few clicker questions before we leave. An open cart rolls along a frictionless track while it is raining. As it rolls, what happens to the speed of the cart as the rain collects? And you're assuming that this rain will fall vertically into the bin, into the cart. Oh shoot. Sorry, we haven't really got to this. I'm going to tell you what the answer is, and then I'll explain. Huh? Does that work? The answer is that it will. What do y'all think it is? It is slow down. That's the answer. Oh. I'm sorry, I was getting a little bit ahead of myself. It is C. So go ahead and put C. I'm going to stop at 1 minute. Who is that? Oh, shoot. Let's just, I don't really have time to do this video. Why don't we just pick up that on Monday, and I'm going to let y'all out. Don't tell anybody that I let you out early, okay? It's like 30 minutes go by. Okay? Y'all have a great week. I always